Section 3.5, Relative Velocity. Our goals here are to derive the relative velocity equation and solve problems involving relative velocity. First, I wanted to remind you of what we did earlier. We have a vector going from point R initial to point R final, and if we define each of these as vectors, R final and R initial, then R from initial to final is equal to R final minus R initial. But let's actually change that. So instead of saying RF, let's make it RFI equals RF minus R initial. And what I'm doing here is I'm making a little notational change that our RFI represents a head, a vector with, let me draw it as a vector. I'll draw all of these with vectors. It has a head F and a tail I. So it goes from the tail I to the head F. Now let me label this point 0 because it's the origin. And I can also say that this vector here is R with the head at I and the tail at O. So I'll put that over there. And this is the vector with the head at F and the tail at O. So it is RFI equals RFO minus RIO. Let's do the same thing here with equation 3.15 and 3.16 with RAB. We have R sub A B equals R sub A E minus R sub B E. And all of these are vectors. And I'm going to just label points A over here and B over here. And E will be the origin. So RAB, remember this is head, tail. Head is A, tail is B. So I will draw that in. I think I'm going to draw that in with a pencil. Hopefully you can see that. So that is RAB. RAE is head, tail. Head is A, tail is E. So that's going this way. And minus RBE. Okay. RBE is head B, tail E. But minus RBE is head E, tail B. Head E, tail B. So I will draw this like this. And then you can see that minus RBE and positive RAE give you R sub AB. Now the same thing works with velocities, but what happens with velocities is that the origin, instead of an origin, we have an entire reference frame of coordinates that are all going the same speed. For instance, the E coordinates here represent probably something like the Earth, the ground of the Earth. Maybe the A stands for the air. Actually, let's not use A as the air. Let's use A as the airplane and change B to W for wind. And then we'll have V sub A E minus velocity of the wind with respect to the Earth. So we can once again put E as the Earth Right now, it's not really. I'm just marking it as a moving point. This moving point of the Earth. Um, so so that might, for it could be any landmark that is attached to the Earth. Any, any landmark that is attached to the Earth has a velocity of 0 with respect to the Earth. Um, and also, with respect to the Earth, the wind has some velocity. Um, so this I will mark as W, and this will be the velocity of the wind with respect to the Earth. Head is wind, tail is Earth, and then we'll put some airplane over here that is moving. A is the velocity of the airplane, and we can see here is the velocity of the airplane with respect to the Earth, and here is the velocity of the airplane with respect to the wind. And again, the W here, this point, represents an object that is stationary with respect to the wind. It has this velocity. So it might be a particle of air, it might be a feather that's somehow caught up and not falling. Could be just a dewdrop or something like that. And the airplane itself is a singular object. But I can erase that stuff so that I can show once again that the velocity of the aircraft with respect to the wind is equal to minus the velocity of the wind with respect to the Earth, which is the velocity of the Earth with respect to the wind, plus the velocity of the aircraft with respect to the Earth, which is this right here. So go that way and then that way, and it's the same as that. Problem-solving strategy for relative velocity problems. Label each object involved. There's usually 3, like wind, earth, air, with a letter that reminds you of what it is. For example, E for earth. Look through the problem for phrases such as the velocity of A relative to B, and write the velocities V sub A, B. So velocity of A relative to B has A first, then B next. The B, you should think of that as your origin. When a velocity is mentioned, but it isn't explicitly stated as relative to something, it's almost always relative to Earth. Number 3, take the 3 velocities you found and assemble them into an equation just like equation 3.16 with subscripts in an analogous order. 4, there will be 2 unknown components. Solve for them with the x and y components of the equation developed in step 3. Alright, one other thing, I'll look at this figure. Figure 3.23 shows the relative positions of 2 cars, but then it says that the rate of change of the resultant vector with respect to time is the relative velocity equation. So for instance, if we had the x component of car 1 being constant or a constant velocity v1 x times t, and the y component being r1 of being v1 y times t, and the second car had equation v2x v2xt comma v2yt, the delta r between them would be, well, it would depend on whether you decided to use with vehicle 2 with respect to 1 or vehicle 1 with respect to 2. So if we decide 1 is the origin car, then we would say 2, 1, head minus tail, so v2x minus v1xt, comma, v2y minus v1yt, and we could say that the v21 was v2 v2 minus v1, really, but both of those are with respect to some origin. We'll say r0 of t equals 0, comma 0. And so what else can I do here? So this is going to be v2x minus v1x, comma, v2y minus v1y. And this is a vector. And that equal sign should carry through. I'm not sure if that cleared anything up, but it's just trying to kind of state what was down here in the text down here in a mathematical fashion.